Bath chemists, welcome to TP's Chemistry Cuts. In this lesson we look at the pH of salt solutions formed in neutralisation reactions between strong acids and strong bases, weak acids and strong bases, and strong acids and weak bases.
I want to start off by looking at what we call a neutralisation reaction and make a clear distinction between this and what we've dealt with so far. So it should be made very clear that when you add an acid to water and water acts as a base by accepting the proton from the acid, that is not a neutralisation reaction. It's the same when you add a base to water like ammonia, you're still not doing a neutralisation reaction. The important part is where you actually form what we call a salt. That's part of the neutralisation reaction. So you're reacting, not adding, you're reacting an acid with a base. This is what you did last year, so we're going back to the same sort of thing that you were doing last year. So if we look at this example, sodium hydroxide is a strong base, you've got a strong acid, and when you add those two together, then you're forming sodium chloride, the salt. So many salts, most salts, are actually metal salts, okay, but not all of them, as we'll see. And what the first thing to take on board is that when you do any neutralisation reaction, there are no exceptions in what we do this year or next year, these are one-way reactions. They are not reversible. Okay? So it's really, really important if you're actually writing out the neutralisation reaction, then you use a single-headed arrow. Okay? That's the first thing to say. What we're going to do is to focus on the salt formed. Okay, so this is the salt here. Because there is a misconception that because these things are formed in a neutralisation reaction, all salts are neutral. As you will see, they're not necessarily. Okay? So, this is a salt. Not all neutralisation reactions produce water, by the way. So I've put that in bracket there. So that's basically a definition of a neutralisation reaction and what we mean by a salt. Okay, let's focus on those. And I'm going to take another look at adding strong acids. I'm going to give an example of a strong acid, a strong base, a weak acid and a weak base, each of which is added to water. Okay? So let's go through this again. Now, the more we do it, the more it becomes sort of second nature. The HCl is the acid because it donates a proton. That means then that water is acting as a base because it accepts the proton. What's this? Compared to that, it's the conjugate base. This is the conjugate base. And this one is the conjugate acid. Now something must be happening that stops the reverse reaction. Something must stop that reverse reaction. And it's the chloride that does it. Okay? So this, if you look at the conjugate base of a strong acid, it's always unreactive towards water. Okay? It doesn't react with water. That's why this is a one-way street. Okay?
Wait, sorry. How do you know that it's unreactive towards water?
Because otherwise it would be a reversible reaction. And it's not.
Oh, okay.
We know that this will always donate a proton back because it does it with weak acids. So it must be this thing that's the problem. So it's this that's not reacting. So it's unreactive. Still the conjugate base, but it's an unreactive one. Okay? So if we look at, and that's the same for NO3 minus, which is the conjugate base of nitric acid. SO4 2 minus, the conjugate base of sulfuric acid. And Br minus, the conjugate base of HBr. Okay. So that's for a strong acid. If we consider a weak acid, and the important difference is this conjugate base is reactive towards water. That's why you get the reverse reaction. Okay? It will react with this more readily, but it will react with water. And then we've got the similar thing with bases. Okay, so I'm going to quickly write both of them out. Now the strong base, remember these are just ionic salts. They're hydroxide salts that just dissolve up and so they separate. So there's no real transfer of protons going on. So we can't really draw that in. But what we are doing is releasing this in solution, which unbalances the H3O OH minus concentrations in solution, and that's why it goes basic. Yeah. Here, you're doing an actual reaction where you're generating this. Okay. And so we can use the transfer of protons as we did before. So this is the acid. This is ammonia, the base with the proton on it. But when it reacts with OH minus, it's donating the proton back. So this is actually acting as an acid. So this is the conjugate acid. And it's the same here. And so the OH minus is the conjugate base of water. So now we've got the complete picture. We can talk in terms of the reactant side, in terms of an acid-base proton transfer, and we look at the side of the products. Then we've got our conjugate. So in the case of our strong acid, you've got our conjugate base, which is unreactive. For a weak acid, you've got the conjugate base that is reactive. But then you've got H3O+, and remember that's the important species that determines that the solution is acidic. So it's about, acidity is about this bit. Okay, now in this case, as above, the conjugate acid of a strong base is not reactive towards water. Whereas the conjugate acid of a weak base is reactive towards water. So the take home from this, or the important part, basically what we've been doing is just using our understanding of acid-base behaviour in terms of proton transfer to label these things. The big take-home message is that first of all, and this is of lesser importance as we'll see, that if you take the conjugate acid of a strong base or the conjugate base of a strong acid, they won't react with water. So the conjugate of a strong thing is unreactive. However, the conjugate of a weak acid, where a weak base is reactive. So this is the really important thing. So we're going to start off with a strong acid and a strong base. Okay? So let's write one out, an example. I'm going to write it out in full. Okay? So the salt, when it's formed, is in solution, so the ions are separated in solution. Okay? So let's put this all the states in to make it clear what we're talking about. Now what we've got is this is the conjugate acid of a strong base. And as we've said already up there, it's unreactive. This is the conjugate base. Of a strong acid, which is again unreactive. So what you've done is you've formed a salt plus water. What we're saying on the board here is that both parts of the salt are unreactive towards water. So they're going to have no effect on pH because they're unreactive. Yeah? This is just water. So what's the pH of the solution going to be? 7, because nothing's going to react with the water to form either OH minus or H3O plus. So if you remove all of that with an exact amount of that, then what you're going to end up with is just this in solution, and that's unreactive, and that has a pH of 7 anyway. So you end up with something that has a pH of 7. Okay, so that's because nothing's reactive. Let's change it round a bit. Okay? In the last lesson, what I've done was I covered the fact of if you look at strong acids, strong bases, weak bases, you add them to water, you form the conjugate. Okay? And we looked at the conjugates of each of the strong acid, strong base, weak base, and we related them to their reactivity towards water, and we linked that to the fact that with strong acids, for example, they're a one-way reaction. They completely dissociate. There's no reassociation. It's just a one-way reaction. And that's because the conjugate base of a strong acid is unreactive. It won't accept a proton back. Okay? So it's just a one-way street. And it's the same with the conjugate acid of a strong base. It won't donate a proton, and so it's a one-way street. Now, when you come to look at a neutralisation reaction between a strong acid and a strong base, what you're in fact doing is forming a salt that's a combination of the conjugate acid and conjugate base of those strong base and strong acid. And we've just said that they're both unreactive. So the salt itself is completely unreactive towards water. Neither the conjugate acid nor the conjugate base will react with water, and so there's no further reaction, so there's no effect on the pH. So it won't actually generate a basic or an acidic solution because both of those ions are unreactive towards water, and so those neutralisation reactions, if you take a strong acid with a strong base and you use an exact equivalent of the two, so you've got none of the acid left or none of the base left in the resulting solution, the salt itself gives rise to a neutral solution. So that's a strong acid with a strong base. What we now are going to look at are these two. a weak acid with a strong base and a weak base with a strong acid. Okay, it's so easy to get these things done. So, the problem we're going to encounter, or the difference we're going to encounter, is when we look at a weak acid, we're going to form its conjugate base. And that conjugate base is reactive towards water. Now, when I say reactive, I don't mean that you put it in water and it starts violently reacting. It just means that a reaction will occur, even if it's only to a very low extent. Okay? So, the weak acid is going to form the conjugate base. The strong base is going to form the conjugate acid, but that conjugate acid we can forget about because it doesn't affect anything, because it doesn't react with anything. Okay? It's unreactive. So, we've got our weak acid, and here's an example of methanoic acid. It's reacting with a strong base, sodium hydroxide, and you form a salt, which I've separated the two ions for because it's in solution. So you've got the anion here, which is this is methanoate, and that is the conjugate base of this weak acid. Okay, and then you're forming sodium plus cation, which is the conjugate acid of the strong base, and that's unreactive, as I said. Okay, and you form water as well. Now the thing that's important now is this is a reactive anion. Okay, and so we can't just ignore it and just say, oh, it's there. It has an effect on the overall solution because it reacts with water. So what we're going to do is actually look at that reaction. It's a base. Bases accept protons. This one is no different. Okay? So if we have this in a significant concentration in solution, it will react and it will have a significant effect on the solution. So here we have that base. It's going to react with water by acting as a base and accepting a proton from it. So let's write that in. That's the transfer of protons from water, which acts as an acid in this case, and the base will accept that proton, and we get this back. And this often confuses people because when we started the initial neutralisation reaction, you think, well, it's here. We've still got it. And the answer is, no, it's not, because when we carried out the neutralisation reaction, we removed it all. We've added an exact equivalent of that, and it's taken it away. This has been formed 100%. Then we can say, right, now we've got 100% of this, none of that, but this is going to react with water. So what's going to happen is it's going to accept a proton from water. You're going to form this, which is its conjugate acid, and you're going to form OH-. Okay? And that makes the solution basic. Okay. So overall, if you carry out this neutralisation reaction, where you add an exact equivalent of these two to each other, you don't end up with a neutral solution. Because you're starting with a weak acid, you form its conjugate base. The conjugate base makes the solution slightly basic. Now, it is only very slightly basic because this is a very weak base. Okay, next year you'll see how they relate, but this is a very weak base. So the pH of this is only slightly above 7. Okay? But it's still measurable, so it is basic. It's not a neutral solution. So if you were to put a universal indicator into this, it would actually go quite blue. Right? If we take this example now, we've added an exact equivalent of a base to an acid, so we've neutralised the acid, shall we say. Okay. What we formed is the conjugate acid of the weak base and the conjugate base of the strong acid. We can ignore that conjugate base of the strong acid because it's unreactive. It's not going to affect the balance of OH- and H3O+. It's floating around in solution as a spectator ion doing nothing. However, this is reactive. Okay? So, if we start with NH4+ in solution, it's the conjugate acid. Acids donate protons. Okay? And so, if we look at a suitable water molecule that's floating around nearby, an ammonium cation will donate its proton, so it's going this way this time. Yep. And so NH4 plus loses its proton to form NH3. And you're forming H3O plus. And because you're forming H3O plus, the concentration of H3O plus is now greater than OH minus, and so overall this solution is acidic. So if you take ammonia and you neutralise it with an exact equivalent of a strong acid, you will actually form a slightly acidic solution. Now, if you look at the Kc values, or they're not actually called Kc values, but they're the equivalent of a Kc value for these, the equilibrium constant values, they are incredibly small. Very, very small. What does that tell you? So for both NH4 plus and for this, if we look at these two, the equilibrium constants are very small. It's reactant favoured. In other words, the equilibrium is way over this way. But there is still a significant quantity of this being formed, and this solution will be basic. This one, again, very much reactant favoured. Talking in tiny, tiny numbers. But there is a significant amount of that in solution, which means that the concentration is higher than OH minus, so the pH is going to be less than 7. Okay? So that's the all-important thing. So, the type of question you might be asked. Let's look at an example. Which one is the most obvious solution? HCl. Okay, so if we look at this one, this is HCl is what? A strong acid. So let's define it, and I've defined it. Let's do an equation. Always write an equation when you're talking about acids and bases, so you can get some idea of what's going on in solution. So, HCl plus H2O, one-headed arrow, okay, very important, Cl minus plus H3O plus. Now we've got to talk about the pH. The pH is all about this. So we've got a high concentration of H3O plus, so you'd expect a very low pH. Okay? Okay? So let's... Normally they'd actually give a concentration. I don't like using concentration at the moment because you don't really have a feeling for what the numbers mean because we haven't done moles and so on. So they'd say something like compare the pH of 0.1 mole per litre solutions. If this was a 0.1 mole per litre solution, then the pH would be, well, because it's minus the log of 0.1. Okay? Now, the next one is this. For me, is the most obvious one to do. What can we say about NH3? It's a weak phase. And this is a partial dissociation, so it's reversible. Okay, so you need to be careful what you say. Don't say it's got a low pH, because it hasn't. It's got a pH of greater than 7. But it's because it's producing OH minus, that means the solution is basic. In other words, the pH is greater than 7. But partial dissociation means that that concentration is quite low. And so although it's above 7, it's still pretty low, or relatively low. Okay? Doesn't mean it's 7 point something, it's usually about, I think, 11. Which sounds high, but it's not. So if we look at the last one, this is where you've got to be careful. Where does F minus come from? How would you form F minus in terms of an acid or a base? Is it going to come from a base, or is it going to come from an acid? If you've got Cl minus, where's that come from? Which acid? So F minus is going to come from an acid, HF. Okay, HF is hydrofluoric acid because it's in the same group as chlorine. Okay, so F minus, I'm just making that obvious. I know it sounds obvious. Now, Na plus AQ is unreactive because that's the conjugate acid of a strong base. So it's the conjugate base of the weak acid HF. It looks really odd, doesn't it? Because normally you talk about chlorides and things, we're talking about something that's unreactive, and suddenly fluoride is reactive. So you get F minus. So if you've got sodium fluoride, okay, it's actually slightly basic. So it's a bit like the ammonia. Okay, you wouldn't be needing to compare the two because we can't do that quantitatively. You haven't done that. Often they'll ask a question like this, and they'll say compare the pH. And in the case of something like sodium fluoride, which is a solid, okay, because it's ionic, it's solid, they'll say use two equations to show. Okay, when it says that, the reason is because you're starting with a solid, okay? So, NaF, any ionic compound, metal plus non-metal, you need to dissolve it up before it can be acidic or basic. Solids don't show acidity or basicity until they're in solution, because they can't donate or accept a proton until there's a water molecule around to make the thing acidic or basic, okay? So you need to dissolve it up first. So that's our first equation. Remember, this doesn't do anything. We've said there, it's unreactive. So that's our first thing when it's dissolved up. So, but this does. So that now reacts with water, as I put above. And so that's the two equations together. Now I put it twice. But that's just to emphasise the point. So if they ask you for two equations, it's because you're starting with a solid and you need to dissolve it up to separate the ions and put them into solution so that they can then either react or not with the water.